Yeah.
Big button moves forward, bottom one moves backwards. Hold on the very top for good.
Okay.
Right. Should be good. Whoever the chair, yeah. Are here. Are you chair?
Yes.
Yeah, I just have to make a couple announcements. Okay, before we get started with the afternoon session, there are a couple announcements. So the first is that tomorrow is a half day. So lunch will not be provided. You're free to go wander into Toronto and get lunch. We will be having an excursion to Toronto Island, which is an island in south of here, and it's nice to walk around and get ice cream, see the sights. For those who want to walk, we'll be leaving here at 1:30 to walk down to the ferry, or you can meet us there at 2:30, and we'll cover the tickets to go to the island. Second announcement is that on Thursday at 6 p.m. we're going to have a reception at the Prenup Pub, which is a pub very close to here. You can look it up on Google Maps. So that'll be at 6 o'clock at the Prenup Pub. And there's another announcement as well.
Yeah, so last year, Sarah started a very nice tradition. So a bunch of people wanted to continue this tradition. And so we figured like 5:15 on Thursday, we can meet downstairs at the entrance of the building and go for a walk. The people who feels like want to join, ask me. Okay, so this is stressful for me, sorry. So we want to address all kind of minorities possible in this community. So everyone is welcome who feel that they need this space. And we just want to walk around the park that is in the center of the University of Toronto. Like there is a very nice park with flowers. And if you like just to walk around and meet people, let's meet on Thursday, 5:15. And from there, we can walk to the reception at 6. Okay, well, whatever, you talk to me and I explain more about this. Bye.
Okay, thank you. And now we'll get started with the afternoon session. Yeah. Bring up the pub.
Okay, so let's begin the last session of the day. So it's my pleasure to introduce Anna Ben-Hamou. She's assistant professor in Sorbonne University. She did a PhD at UPC, so University of Paris-Cité, and a postdoc at IMPA in Rio de Janeiro. And her domain of expertise are probability and statistics, and she's a specialist of let's say random walks on groups on graphs and mixing time, and she will talk about mixing time of a matrix random walk.
Thank you very much. And yeah, thank you also to the organizer. It's really a great pleasure to be here at this conference. So yeah, in this talk, we're going to look at a particular random walk on binary matrices, invertible binary matrices, and more precisely, we'll be interested in the mixing time. So I will try to go slowly, explain everything, and so yeah, hopefully everyone can follow all through the end, but if something is not clear, feel free to interrupt me. Okay, so the random walk, so the Markov chain we're gonna look at is the following. So the state space will be the set of invertible binary matrices. So matrices, so n by n binary matrices that are invertible in Z2. And the dynamics is as follows. So at each step, we will pick uniformly at random 2 distinct rows. and we will add one to the other in modulo 2, okay? So here, let's say that I pick row I and row J, then at the next step, so row J doesn't change, but row I becomes row I plus row J, okay? And so the transition matrix of this chain is simply the following. So the probability to go from some matrix X to some other matrix Y is just 1 divided by n times n minus 1 if I can obtain Y from X by multiplying by I plus EIJ, so where EIJ is just the matrix with 0 everywhere and 1 in position IJ. Okay, so it's really mean adding row J to row I. And I have 0 if I cannot obtain Y from X this way, okay? So what can we say about this, this matrix? So first, we can observe that it's symmetric, okay? Pxy is equal to Pyx. And this implies that the uniform distribution over omega is an invariant distribution for the chain. So in the sense that if I start from the uniform distribution and apply the kernel P, then I remain uniformly distributed, okay? And yeah, so let me here maybe say a word about the size of this set omega. So it's, you can actually observe that it's a constant fraction of all binary matrices. Okay, so here, if I look at the ratio between the size of omega and 2 to the n squared, so the number of binary matrices, so it's just the probability that a random binary matrix is invertible. I can just decompose this probability by sequentially looking at every row. So if I look first at the first row, the only event that will prevent the matrix from being invertible because of this first row is that it's the 0 vector. And so this has probability 1 divided by 2 to the n. And then I go to the second row, say, so conditionally on the fact that the first row is not the 0 vector, then the bad event would be either to be the 0 vector or to be equal to the first row. So I have 2 divided by 2 to the n. Then if I go to the chaos row, I don't want to be a combination of the first k minus 1 rows. So I have 2 to the k minus 1 bad possibilities. And so in the end, yeah, okay. And then for the last row, I just have a 1/2 chance to make the matrix invertible. So I get this product here. And so, okay, if we approximate this, we, as n tends to infinity, we get some number which is just below 1.3. And so, okay, so let's keep in mind that the size of our state space is a constant times 2 to the n squared. Okay, now, second observation about the matrix, it's that those matrices here, I plus EIJ, so by the way, they are called the elementary transvections, they generate the group omega. And so this means that the chain is irreducible. So it connects every pair of invertible matrices. And this implies that the uniform distribution is the only invariant distribution. Okay. And last, last fact about this matrix, it's aperiodic. So it means that you cannot partition the state space into 2 subsets such that the chain alternates between each of them, okay? And this property of aperiodicity ensures that the chain will actually converge to the unique stationary distribution pi. So in the sense that starting from any matrix X in omega, if I look at the probability to arrive at some Y after T steps, then this converges to pi of Y, the stationary probability. Okay, so now what is our goal? Our goal is to study the speed of this convergence. So what we would like to know is after some given number of step T, how close I am from the uniform distribution, okay? And so, of course, to give sense to this word, how close or how far, I have to take a distance between probability distributions, okay? And so for probabilists or statisticians, the canonical choice for distance between probability distribution is the total variation distance. So if I have two probability measure, mu and nu on omega, the total variation distance is just the maximum over all subsets of the absolute difference between the two probabilities. And so the function that we will be interested in is the function d of t, which is the total variation distance between the low of the chain at time t and the uniform distribution. So of course, when I say the low of the chain at time t, I have to specify a starting point. But it turns out that in our case, the chain is transitive. So roughly speaking, the underlying graph looks the same from every point. And so the starting point does not really matter. And we can just consider that we start at the identity matrix I. Okay. And now the mixing time is defined as follows. So it depends on a parameter epsilon between 0 and 1. And so the epsilon mixing time is just the first time t when d of t falls below the threshold epsilon. Yeah, maybe something I can mention is that this function d of t is between 0 and 1. At time t equals 0, it's very close to 1. And then it's decreasing, okay? And we know that it tends to 0 as t tends to infinity, okay? So okay, in particular, once I know that d of t is less than epsilon, then the distance will remain below epsilon for each later times. And another remark is that in this talk, the precise value of epsilon will not really matter. So indeed, if we are only interested in the order of the mixing time in terms of n, then the choice of epsilon does not really matter. So more precisely, for every epsilon prime between 0 and 1/2, the epsilon mixing time is of the same order as the epsilon prime mixing times, okay? So, so to fix ID, we will just fix epsilon to be 1/4 and define T mix as a T mix of 1/4, okay? Okay, and so, yeah, before presenting the known result about the mixing time of this matrix van der Mook, let me first say that this chain has some cryptographic motivations. And in particular, so it has been used in a particular class of authentication protocols, which are known as time-based authentication protocols. So in an authentication protocol, you have a prover wants to prove its identity to a verifier. And for time-based authentication protocol, the authentication is successful, not only if the prover gives the right answer, but if it if it provides the correct answer fast enough. Okay, and and in 2016, Sotiraki proposed the following protocol. So the prover will start at the identity matrix and will run the matrix chain up to some time t, and this will create a matrix, say A, that will be made public and that will act as a public key. And then each time the prover wants to authenticate, he will ask the verifier for a vector, a binary vector of length n, and the challenge is to compute y, the product of A and X. Okay, so okay, what happens is that the prover knows the trajectory of the chain. So to answer the question, he can just apply the same row operation that he did for the matrix to the binary vector X and provide the correct answer in time t. But now for a dishonest party, so someone that is not the prover, we can observe that if t is large enough, then the dishonest party might struggle to distinguish the matrix A from a completely random matrix, at least in polynomial time. And so in this case, its best solution would be to just perform usual matrix vector multiplication, which typically takes time n square. Okay, so this protocol would be successful if t can be chosen much smaller than n square. And so here, okay, let me maybe point out that the talk will not really answer this question, because here it's actually a question about what's called the computational mixing time, okay, because in a way it's the time when you cannot distinguish the matrix with a uniform one by using only test functions that are computable in polynomial time, whereas the talk will be about the mixing time in the sense the information theoretic mixing times, okay? But okay, this was just to give some motivations. So what's known about the mixing time of the chain? So let's first look at the lower bound, and you will see that so this will be the best known lower bound, and it really comes from a very simple counting argument, which goes as follows. Let's take A to be the subset of matrices that the chain can attain in t steps, okay? Starting from the identity matrix. So by definition of the total variation distance, d of t, which is the maximum of the whole subset, is larger than the difference between, so PTIA, the probability starting from I to be in the subset A at time t, minus the stationary probability of A. So PTIA is 1 by definition of A, and pi of A is the size of A divided by the size of omega. But now we can just observe that the underlying graph of the chain has degree n square, okay? Because at each step I choose 2 distinct rows, okay? Has degree n times n minus 1. But so the size of A, I can just say that it's less than n square to the power t, okay? Because at each step I can see at most n square new matrices. And the size of omega, we have observed that it's of the order 2 to the n square. And so if you just use this and invert the function d of t, you obtain that the mixing time is the order of the mixing time is larger than n squared divided by log n. Okay. Now for the upper bound, so the various like upper bounds that were obtained for these chains all rely on a spectral notion, which is the relaxation time, and which can be defined as follows. So it corresponds in a way to the asymptotic exponential rate of decay of the function d of t. More precisely, so if you take d of t and raise it to the power 1 over t, then it converges to a spectral quantity, lambda star, which is just the maximum in absolute value of all the eigenvalues of the matrix P. And so, this means that for t very large, d of t roughly behaves like lambda star to the t, so roughly exponential minus 1 minus lambda star times t. And so this leads to consider the relaxation, to define the relaxation time as 1 divided by 1 minus lambda star. So 1 minus lambda star is called the spectral gap, and the relaxation time is just the inverse of the spectral gap. So it's
You meant to say lambda not equal to 1.
oh, right. Yes, sorry. This is important. Yeah, so 1 is always an eigenvalue of P, and here, yeah, we look at eigenvalues different from this one. Thank you. Yeah, and so for our chain, which is irreducible and aperiodic, it guarantees that this lambda star is strictly less than 1. So the relaxation time is well defined. And so, yeah, so basically it corresponds to the time scale that is needed asymptotically to reduce the total variation distance. And yeah, so I will mention some connections. So yeah, I mention it because we will use it later. This relaxation time is related to the notion of Poincaré inequality. So yeah, anyway, we say that the matrix P satisfies the Poincaré inequality with constant given by the relaxation time. So it means that for all real valued functions on omega, the variance of the function f under the stationary distribution can be bounded by the relaxation time times the Dirichlet form of f, which is just defined as, so 1/2 times, so here you see that we choose a pair xy, we choose x according to the stationary distribution, and then y according to pxy, and we look at the square difference of f of x minus f of y. So this Dirichlet form can be understood as a local variance of f along the edges of the underlying graph of P. And so having a Poincaré inequality with a small relaxation times means that the local variance already takes a good fraction of the global variance. Okay, so it goes in the direction of mixing more quickly. Okay, but just, yeah, let's keep this in mind for later. Right now, what is interesting for us is the following inequalities that relate the mixing time and the relaxation time. So the mixing time is always larger up to constant than the relaxation time, and smaller up to constant than the relaxation time times the logarithm of the inverse of pi mean, which is the smallest stationary probability. So for us, pi is just the uniform. So 1 over pi mean is just the size of omega. And we have said that the size of omega is for the 2 to the n square. So with the log, this will give us a factor of n square between the mixing time and the relaxation time. So so yeah, the first result for this chain is from Diaconis and Saloff-Cost in 1996. They showed that the relaxation time is big O of n square. And so, by the way, this is the, I think, one of the first example of the comparison techniques that they developed to compare Dirichlet forms of different Markov chains. And so by the inequalities that we just mentioned, this gives a bound of big O of n to the 4 for the mixing time. Then, Kasabov improved quite drastically the bound on the relaxation time. He showed that the relaxation time is actually big O of n. And yeah, this is really a very powerful result and very impressive. So this means that the order of the relaxation time is actually the same as if the columns of the matrix were evolving independently. And this implies that the mixing time is big O of n to the 3rd. Okay, and so, okay, so at this point we have a lower bound of n squared divided by log n, and an upper bound of n cube. And so, yeah, we would like to know what is the right order. So let me mention that there are converging heuristics that tend to support the fact that up to log factor n squared should be the right order. And so this question was actually suggested to me by Yuval Perez now about 10 years ago when I was an intern with him. And so we were not able to make any problem on this matrix work. So we decided to study more precisely the dynamic of the first column of the matrix. So if you look at the first column, you can observe that the dynamic restricted on this first column is still a Markov chain. So it's a Markov chain that evolves on the hypercube 0, 1 to the n minus the 0 vector. And the transition are just, so if the current state is some vector x, then you choose a pair ij of distinct coordinates, and you replace xj, so the bit at j, by xj plus xi, mod 2. And so Chung and Graham showed that for every epsilon between 0 and 1, there is a constant C epsilon such that the mixing time of this chain is smaller than C epsilon times n log n. And in this paper, they asked whether the dependence in epsilon could be removed. And so with Yuval Perez, we answered this question positively by showing that, that actually for any epsilon between 0 and 1, the epsilon mixing time is asymptotically equivalent to 3/2 n log n. And so, so someone familiar with mixing time knows that this is known as the cutoff phenomenon. So it means that, okay, maybe a small picture. So you see that the first order of the mixing time, of the epsilon mixing time, does not depend on epsilon. And an equivalent way to say this is that if you look at the distance d at the scale 3/2 n log n, so I will look at d at times c times 3/2 n log n, and here I have c. Then asymptotically, when n tends to infinity, what I will observe is just an indicator. It will be 1 if c is less than 1, and then 0 if c is larger than 1, strictly larger and strictly smaller. Okay, what happens at 1 exactly is more complicated, but yeah. So the cutoff phenomenon really correspond to a very abrupt drop in the distance to stationarity, where you remain, so you basically do nothing for a long time, and then abruptly you're completely mixed, okay? And to give the basic intuition for this result, so you can see here that for this first column chain, the starting point does matter. And so we can guess that the worst starting point is to start at a vector that has a lot of zeros. And so for starting from the vector that has just a 1 and then all 0, it will first have to add 1s in the vector, okay? And this will take some time. So you will need a time n log n to have enough 1s, so a linear, a constant fraction of 1s in the vector. And then once you have enough 1s in the vector, then you start behaving like just a lazy random walk on the hypercube. So what is that? It's just you on the hypercube at each time you choose a coordinate uniformly at random and randomize it. So 0 with probability 1/2, 1 with probability 1/2. And so this chain is known to have cutoff at n log n over 2. It's actually one of the very first example of the cutoff phenomenon. And it's due to Aldous in '83. And so altogether, this would say that for this chain, the mixing time should be 3/2 n log n. Okay. Okay, and now, yeah, I will just mention that both the matrix chain and the first column chain belong to a larger class of dynamics that has been introduced by Aldous again, and which is known as the product replacement algorithm. So it goes, it's defined as follow. You consider G a finite connected graph of size n, so on n vertices, and a finite group gamma. And then, so initially, you put, so each vertex v in the graph will receive a label given by an element, sigma of v, which is an element of the group, okay? And you assume that the set of labels in the graph, so the set of sigma v for v in the vertex set generates the group. And then the evolution, the dynamic is to, at each step, pick a directed edge, UV, and replace sigma V by sigma U plus or minus sigma V with probability 1/2, 1/2. Okay, and so yeah, this may be used to obtain a random generating set of the group gamma. And so another result that I have to mention is the result of Perez, Tanaka, and Zai in 2020. They showed that, so for any finite group, so here finite is not really what I mean. I mean, if the size of the group does not depend on n, okay? The size of the group is fixed. Then the product replacement chain still has cutoff at 3/2 n log n, okay? So, so same as the first column walk that we just looked at. And in particular, coming back to our matrix walk, this means that I can take any fixed number of columns and look at the dynamic restricted to this fixed number of columns. I will still have cutoff at 3/2 n log n. Okay, and okay, so now, so coming back to the mixing time of the matrix walk, what is really tempting now would be to say, okay, if I know that one column and even any fixed number of columns mixes in order n log n, the matrix walk should mix in n square n log n, big O of n square n log n, because I can just wait for the first column to be mixed and then the second, etc. The problem is that this argument does not work because mostly because the columns are not independent, so you cannot separate the mixing in each columns. So it doesn't work. But it turns out that the heuristic is still so valid, and so we will now see that the mixing time is indeed big O of n square n log n, n square log n, sorry. And to do this, I will need to introduce yet another notion, which is the log Sobolev constant. So, okay, we have seen the Poincaré inequality, and so log Sobolev inequality belong to the same class of functional inequalities, except that, so recall that for the Poincaré inequality, we had a bound between the variance of f, an upper bound in terms of the Dirichlet form of f. Now for the log Sobolev inequality, it will relate the entropy of f square and the Dirichlet form. And the log Sobolev constant is defined as the smallest constant c, such that for all real valued functions in omega, the entropy of f square is less than c times the Dirichlet form. Okay, so how is it related to mixing times? So it turns out that the log Sobolev constant gives you a strong control on the decay of relative entropy. So in the sense that if you look at the relative entropy between some measure mu and the stationary distribution pi, and if you apply the kernel P to the measure mu, then the relative entropy decays by a factor equal to 1 minus the inverse of the log Sobolev constant. And if you iterate this, you have that you start from an initial measure mu 0 and apply the kernel P t times and look at the relative entropy with the stationary distribution, then this will be smaller than the initial relative entropy. times 1 minus 1 over the log Sobolev constant to the power t, which you can further bound by this, because the worst starting distribution for mu 0 would be here to put all the mass on an element that has the smallest possible stationary probability. And this will give you, and so the initial relative entropy in this case would be log of 1 divided by this pi min, okay? And now we have to relate this with total variation, and this can be done using Pinsker inequality that tells you that the total variation distance square is less than twice the relative entropy. And so if you use this, you obtain that the mixing time is less up to constant than the log Sobolev constant times log of 1 over pi min. And so recall that with the relaxation time, the factor was log of 1 over pi min, which was in our case n square, log of 2 to the n square. But now with this log, we would just get a log n factor. So what we need to show now is that the log Sobolev constant of the chain is big O of n square. And so let's do this. So you will see that the proof is quite simple, and that the main ingredient that has all the difficulty is Kasabov result on the relaxation time being big O of n. So yeah, but so let's go. So what do we want to show? We want to show that for all functions f, the entropy of f square is less up to constant factor than n square times the Dirichlet form. So let's consider, let's take some function f, and let's consider the extension of f over the whole set omega star of all n by n binary matrices. And so how do we extend the function? Well, for any binary matrices, g of x will be either f of x, if x is invertible, and otherwise it will be equal to the expectation of f under the stationary probability. And okay, so if you use a characterization of entropy, a variational characterization of entropy, you can easily see that the entropy of f square under pi, the uniform over invertible binary matrices, is less than, so this constant 1 over mu of omega, times the entropy of g square under mu, the uniform distribution over now all binary matrices. So why is it, why does it help to do this extension? It's that now the rows are independent under the measure mu, which is just uniform on all binary matrices. And so this independence is quite enjoyable, because now I can use a property which is called the subadditivity of entropy for product measures, so for independent random variables. And it goes as follows. It tells you that the entropy of g square under mu is less than the sum. So I sum here on each row, and I look at the expectation of the conditional entropy of g square given every rows except row I. Okay, so this entropy here is a random variable of Lj for j different from I, and it corresponds to, so I fix every row and I just look at the entropy corresponding on to the row I. So, okay, so what can happen? So now if I fix a row I, and I condition on so all the rows except row I. So of course, because now I'm on this larger space, if the family Lj does not span a subset of dimension n-1, then whatever the value of the highest row, I will not get an invertible matrix. And so I will not be in omega. And so G, in this case, is a constant equal to the expectation of F under pi. So, so the conditional entropy is 0, because in this case, the function is a constant. And now, otherwise, I can just complete this family Lj for j different from I with some additional vector Li to obtain a basis. And now the law of the conditional law of capital Li, my random variable, is then just that of the sum of Aj times Lj, where Aj is just a uniform binary vector, so IID Bernoulli 1/2. Okay, so in this case, the randomness is just that of a random element of the hypercube. And it turns out that there is a log Sobolev inequality for the uniform measure on the hypercube, and it tells so you have to trust me, but it says that so this conditional entropy in this case can be bounded by so 1/2 times the sum so for all j of this expectation here, where you have here so g of x minus g of xij, which corresponds to just flipping aj, the coefficient aj. So, and in other words, it means that rho li will be replaced by li plus lj mod 2. Okay. Okay, and so this is nice because it starts to resemble the Dirichlet form, but the problem is that it's the Dirichlet form of G, and we would like to come back to F. Okay, so how do we do this? So here I just repeated the same inequality from the previous slide. So we have 3 different situations here. The first situation is that the matrix X is in omega, so it's invertible. And if you come back, so what does it mean to be invertible? It would mean that the coefficient AI has to be equal to 1, because otherwise it will be in the subset spanned by the n-1 other rows. Okay, so either X is invertible, this means that AI is equal to 1, and in the sum I choose J different from I. Then I just flip Lj, so either I add it or D add it, okay, but in any case, I will still remain invertible because AI will still be equal to 1. And so in this case, I can replace G of X by F of X, G of Xij by F of Xij, and I recover the Dirichlet form of F. Second situation is that X is not invertible, so AI is 0, and I choose J different from I, then the matrix Xij will still not be invertible. Okay, so both g of x and g of xij will be constant, the same constant, and so I will get 0 in this case. And the third situation is that j equals y. And in this case, this will correspond to moving from ai equals 1 to ai equals 0. And so I will have one of my two matrix invertible, the other not. And so, and what will appear is actually the variance of f. Because one of my, so okay, there could be two situations, but it's symmetric. But let's say that x is invertible, so g of x is f of x. And then if I flip ai, I will get a non-invertible matrix, and so I will get the expectation of f squared. So it gives me the variance. So altogether, what I get is this. And if I just rewrite this more simply, I obtain this, that the entropy of f squared is less than n times a minus 1 times the Dirichlet form of f plus n times the variance of f. And now I can recall that Kasabov result says that the relaxation time is big O of n, and that the relaxation time gives me the Poincaré inequality, saying that the variance of f is less than n times the Dirichlet form of f. And so I get my big O of n square bound. Okay. Okay, so yeah, so I'm basically done. Just maybe a few open questions, natural open questions now. The first is, can we close the gap between the lower bound n squared divided by log n and the upper bound n squared times log n? And so the question after that would be, does the chain have cutoff? Okay, if we are able to determine the right order, can we now look at the precise constant in front of this order and maybe show cutoff for this chain? And yeah, let me also mention, so I'm not aware actually of any results concerning computational mixing time, but I think it would be a nice thing to look at is what if I look at mixing times for test functions that are computable in polynomial time, and so to come back to the motivation of time-based authentication protocols. Yeah. So yeah, that's it. Thank you.